Hi, everybody. In this video, we're going to start looking at the three-dimensional shapes of certain molecules. If you recall, when we were looking at or talking about ionic versus covalent compounds, we had talked about how ionic compounds and the formula for an ionic compound really just gives the ratio for how the ions are going to be arranged within their ionic lattice. And so most all ionic compounds, if you look at them at the molecular level, look kind of like this. And so this would be an example of NaCl, and that formula gives us the ratio of one sodium to one chloride ion. And so it would look pretty much like this at a molecular level, with the sodium and the chlorine ions alternating with each other. With covalent compounds, however, sometimes called molecular compounds, the chemical formula actually gives us the number of each atom in a discrete molecule. And by discrete molecule, I mean, for instance, something like glucose, C6H12O6. That formula tells us that formula tells us the ratio for one glucose molecule, which would exist as its own entity, which would exist as its own thing. There would be 6 carbon atoms in there, 12 hydrogen atoms, and 6 oxygen atoms. And so what that can end up meaning for molecular compounds is they end up adopting a very certain three-dimensional shape. And so these compounds are not simply flat. They're not simply two-dimensional flat compounds. What ends up happening is they actually adopt a three-dimensional shape based on their electron arrangement. We're going to use Lewis structures that we saw and talked about in the last video, and hopefully you've been practicing. We're going to use Lewis structures in order to determine what this three-dimensional shape of a molecule is. The three-dimensional shape is determined by something called valence shell electron pair repulsion, or VSEPR theory. What VSEPR theory tells us is that the electrons that are in a molecule, whether they are bonding or non-bonding electrons, the electrons will assume a geometry that allows them to get as far apart from each other as possible. Remember, electrons are negatively charged, so they're going to tend to want to repel each other. And so all of the electrons that are in a compound are going to want to repel each other in some way, which ends up leading to a three-dimensional shape that allows for the most space between the electrons. And so, for instance, when we take a look at this here, so let's say that our Lewis dot structure shows us that there are 4 groups of electrons around our central atom. And so, for instance, if we have a molecule, a very simple molecule like methane, CH4, we write our Lewis structure, and we get this. And so 4 groups of electrons, so these are all our electron groups, they happen to be all bonding pairs, 4 groups of electrons around our central atom. Those 4 groups will want to spread themselves out as much as they possibly can. And so they can't be simply 2 dimensions. It can't be the mouse is merely messing with me. It can't be 2 dimensions like we see on the whiteboard here, where this carbon is here and hydrogen carbon sort of this angle 90 degrees as it's written on the paper. It's not going to exist that way. We're going to stretch out in 3 dimensions in order to maximize this angle, in order to maximize this space here. And so if there are 4 electron groups, what the molecule will actually do is adopt a 3-dimensional shape that looks like this. And so you can see, oh, I grabbed the wrong one. This is not the one I want. Let me pause it for just a moment. All right, and we're back. This is the one that I wanted here. And so when we take a look at the 3 dimensions of this, let's see if I can hold it in a way that you can sort of see it. So you can picture these 2 sort of being in the same plane as each other. So these 2 are in that same 2-dimensional space. This one, however, is coming straight towards you, straight towards the screen. This one is coming back. And so it's stretching out into those 3 dimensions that actually allows us to get the maximum space between all electron groups and adopt what we call a tetrahedral formation, which actually gets us to bond angles of 109 degrees plus or minus, but basically 109 degrees in between all of the atoms. So this is a 109-degree bond right here. Let's say we have 3 electron groups only around our central atom. And so this would be an example here. So there are just 3 electron groups around our central atom. And so maybe this would be, for instance, if we have BF3. So if you do out the Lewis structure for BF3, woo, technology is messing with me this morning. So here is our Lewis structure for BF3. And again, we're going to look at our central atom, and we see that we have 1, 2, 3 electron groups around that central atom. And so in order to maximize that space between them, now all of those are going to be in the same plane, but they're going to make basically, picture like peaks of an equilateral triangle, pretty much. And so that will then give us 120 degrees for this bond angle here. And that maximizes the space between all of the elements, or between all the electron groups in particular. Let's say we have CO2. So there's our Lewis structure for CO2. We have 2 areas of electrons. Sorry, there it is. 2 areas of electrons around our central atom, those double bonds from carbon to oxygen. And so we have those 2 groups of electrons, 2 areas of bonding electrons. In order to maximize that distance, those are going to get into what we call a linear shape with a full 180 degrees forming this angle. So that's the whole idea behind VSEPR and behind VSEPR theory, is that molecules will always adopt, or sorry, the electrons for now, we're going to get into the molecule shape in a minute, but the electrons in a molecule will always orient themselves such that the distance between those electron groups is maximized. And so that will necessitate some sort of 3-dimensional shape. And then that shape is going to be dictated by how many groups there are. And then that'll end up playing a role in how the atoms are positioned too, which we'll get into in just a second. And so we can use this electron geometry to predict the shape of the molecule itself. This is where we have to make a distinction between what we call the electron domain geometry, which is just a look at how all of the electron groups around a central atom are arranged. But we have to remember that we don't always have just bonding groups around a molecule, around a central atom. Let's look, for instance, at the Lewis structure for ammonia, for NH3. So we end up with a structure that looks like this. So in this structure, we absolutely have 1, 2, 3, 4 electron groups around our central atom. And so the electron groups will definitely arrange themselves something like this. However, not all of those electron groups are bonding groups. And so the electron domain geometry in an example like this, so the electron domain geometry is tetrahedral, that word that I used earlier, and we're going to look at these words, this terminology a little bit deeper in a second. But the actual molecular geometry, how the atoms are arranged. And so electron domain geometry is how are all of the electron groups arranged around the central atom. But the molecular geometry is how are all of the other atoms arranged around our central atom. And so in the case of ammonia, one of these electron groups is a non-bonding group. The actual atoms look like this. And so the molecular geometry is different, and it's something that we call trigonal planar. When the central atom has only bonding groups and no non-bonding groups, the molecular geometry, the molecular shape, and the electron geometry are the exact same. And so in the case of the methane, CH4. So remember what CH4 looked like. We'll just redraw it real quick. So 4 bonding groups around our central atom, or 4 electron groups rather, around our central atom. They're all bonding groups. And so the electron domain geometry is tetrahedral, and the molecular geometry is tetrahedral. And so if all of the electron groups around the central atom are bonding, your electron domain geometry and your molecular geometry will be the same. If, however, you have non-bonding pairs, and so in a case like ammonia, so here's ammonia, and here now we're showing the lone pair. And so here's our ammonia from before. Just bring this back. So we have our nitrogen here in the middle, our H, our H, and our H. But then we also have this lone pair up top. And so we can see that our electron domain geometry is still tetrahedral, just like methane was. We have 1, 2, 3, 4 electron groups, but only 1, 2, 3 of those are bonding groups. And so our molecular geometry is not the same as our electron domain geometry. And the shape, the actual molecular geometry, the shape of the atoms in a molecule is defined by the position of the atoms, not necessarily all the electron groups. And so in trying to differentiate this and trying to see, okay, what shape does my molecule actually have, your first step is always going to be to draw the Lewis structure. You have to be able to draw a proper Lewis structure in order to figure out the three-dimensional shape of a molecule. From there, you can use a chart like this, and this is just a blown up version of one with some extra information on it. I'll show you some others that you're going to use for your purposes later. But you can see in a chart like this, that, oh, here we go. Keep my hands off the trigger, so to speak. And so what you do first is you look for your total number of electron groups around your central atom. And so in the case of methane, we count 1, 2, 3, 4 electron groups. Now, when you're doing this, double or triple bonds count as 1 electron group. You're looking for areas where there are electrons. And so in a case like CO2, so here was our Lewis structure for CO2, we would count 1, 2 electron groups. We're just looking for areas where there are electrons, not the total number of bonds, just areas where there are electrons. And so in our methane example, 1, 2, 3, 4 total electron groups. Anytime that you have 4 total electron groups, the electron domain geometry is going to be what we call tetrahedral. But then to find the molecular geometry, we want to see how many of those electron groups are bonding and how many are non-bonding. If none of them are non-bonding, if they are all bonding groups, then your molecular shape is also tetrahedral. If, as in the case of ammonia, 1, 2, 3, 4 electron groups, 1, 2, 3 of those are bonding, 1 of those is non-bonding, then we still have an electron geometry of tetrahedral, but now a molecular geometry that we call trigonopyramidal. Lastly, for our tetrahedral electron geometry, this would be what water would look like. So we do up our Lewis structure of water, H2O. We would get this. And so we can see that we definitely have 1, 2, 3, 4 electron groups around our central atom. So it's a tetrahedral electron domain geometry, but 1, 2 of those are bonding groups, and 1, 2 of those are non-bonding groups. And so we have what we call a bent molecular geometry, called such because if we don't even bother looking at our lone pairs, this is what the shape of a water molecule really looks like. So we can see that bent shape of our overall structure when we look at just the atoms. And then we can look at some others. If we have 3 electron groups around our central atom, so this would be right here would be an example of our carbonate polyatomic ion. And I would encourage you to do the Lewis structure of that out yourself. Go ahead and pause the video. Do the Lewis structure of CO3 2 minus. You would see it looks something like this. And so we have 1, 2, 3 bond, or 1, 2, 3 electron groups, giving us an electron geometry of trigonal planar. In this example, all 3 of those are bonding groups, no non-bonding groups, no lone pairs, and so our molecular geometry is also trigonal planar. In the case of, I do have one. Here we go. In this example here, maybe something like sulfur dioxide, like is seen on your screen. We have 1, 2, 3 electron groups, so it's still a trigonal planar electron geometry, but only 1, 2 of those are bonding groups, and 1 is a non-bonding group, leading us to, once again, a bent molecular geometry. And so you'll always use a chart like this in order to actually determine your shapes. When you're drawing this, by the way, so as another note here, let's just bring this back up. So if we're drawing out maybe our methane with our CH4, your typical Lewis structure gives you information about how all the atoms are actually attached to each other, but it doesn't give you any information about the actual 3-dimensional shape. We have to use our Vesper chart for that, figure out what the actual shape is, but then we do have a way of redrawing it to help us out with that 3-dimensional shape. So if we wanted to actually draw this and depict what it does look like in 3 dimensions on a 2-dimensional sheet of paper, we would draw it like this. We would have there's our C and 2 of our H's. So if I'm holding it like this, then there we go. You can sort of see it now. So here's 1 H, which would be equivalent to this H up here, and then down to the carbon, and then down to the other H, this one right here. So those are all 3 in the same plane. But now I'm going to draw the one that's coming out towards you. So this one's coming out towards the screen, and I depict that with a wedge. So this wedge here means that this is coming out. So that's coming out at you. But then we also have the one that's coming back towards me. So this one's pointing back towards, coming back towards me as opposed to towards you. And we draw a dash. That means that it's going back into the plane, or back into the paper, back into whatever you're drawing. And so this allows us to start thinking in 3-dimensional terms, and allows us to start thinking about the 3-dimensionality of the molecule. This is another chart that I just kept in the slideshow. This is one directly from your book, but this one walks us through electron domain geometries of 2, 3, and 4. And for 2 electron groups, we're only ever going to have 2 bonding groups and no non-bonding. That's going to give us a linear structure, something like CO2 or hydrogen cyanide that you see on the sheet. And we went through the 3 and 4 already. This is one that I put together a couple of years ago, and you do have this right on the website. This is just the link to it here, but it brings you to the full actual Vesper handout. Again, if you just go to the website, if you go to molecular geometry, polarity, and intermolecular forces, materials, so just down here in topic details, this is the topic that we're talking about right now. So materials for this, and then, oops, I'm pretty sure I've updated this. Let's give it a bit of a refresh here. Oh, maybe not. This isn't supposed to have 2 of them. Sorry, I'm talking through things as I do it. Oh, no. Oh, yeah. No, hold on. Let me pause you for just a second. Sorry about that. And we're back. I just hadn't hit publish on my working website yet. And so 2 informational handouts. One of those, just the Vesper handout. That brings you to a little bit of an explanation as well about Vesper, a lot of the things that we've just talked about. but then a copy of the handout, but also Vesper chart only on that materials page just does bring you to the actual handout. So let's look at how we would use that. This is just the first half of it on this first slide. And so here you're going to count the number of electron groups around your central atom. So you're going to do your Lewis structure, count up how many electron groups you have around your central atom, and that will tell you basically what category of electron geometry you're in. Is it linear, trigonoplanar, tetrahedral? If you have even more, you might have 5 groups around your central atom. That would be a trigonal bipyramidal electron geometry. I think that was one that I had earlier. Yes, it was. So 5 groups here around our central atom. You can see 1 here and here, and then 3 around in the middle there. Or even up to 6 would be what we call an octahedral electron geometry. But then what you've got to do is count up how many of those are bonding and how many of those are non-bonding, and that will lead you to the molecular geometry as well. And you can see that here on the second part of the sheet. Not only that, but it also goes on to tell you what the bond angles are. And so, for instance, the bond angle here is ammonia here. And so we have 1, 2, 3, 4 electron groups, but 1, 2, 3 of those are bonding. So it's a tetrahedral electron geometry, trigonal pyramidal molecular geometry, and the bond angles are a little bit less than 109.5. And so this angle here, hydrogen to nitrogen to hydrogen, bond angle of a little less than 109.5. And so that's how we figure out the three-dimensional shape of a molecule. If we have a molecule that's a little bit bigger, and we might have what we call 2 central atoms in there, those we just think about the molecular shape 1 atom at a time. So we would think, in this example of methanol, we would think about our molecular shape around this carbon and a different molecular shape around this oxygen. Now we also have polarity. And so within our compound, each of the atoms that are in covalent bonds, each of those atoms will attract the electrons in the bond a little bit differently. And that's what electronegativity measures. Electronegativity measures how much is the atom drawing the electrons towards it. And so are the electrons spending more time near one of the atoms than another? The higher an electronegativity, the more time that electrons spend towards that atom. And this, you can see what our trend is here. As we look at the periodic table, electronegativity increases as we move up and to the right. We don't really consider the noble gases because those don't participate in bonding really. So that means that fluorine is our most electronegative atom. And so if we have a bond between, say, carbon and fluorine, then the electrons in that bond spend more of their time closer to fluorine. What that does is that builds up what we call a partial negative charge on the fluorine atom. The carbon atom in that case would have what we call a partial positive charge. So we can see a good picture of that here. So this would be maybe our carbon and our fluorine. The electrons are getting pulled towards the fluorine a little bit. Or sorry, the opposite, high density in red. Here's the fluorine here, here's the carbon. So the electrons are getting pulled towards the fluorine. So we have more of an electron buildup here. And you can see here is how we depict that. This arrow with a little plus sign. And so in this example here, oxygen definitely has a much higher electronegativity than carbon does. And so the electrons are getting pulled towards the oxygen atoms and spending a little bit more time near the oxygen atoms than they do the carbon atoms. And so we have what we call 2 polar bonds, from carbon to oxygen here and carbon to oxygen here. In boron trifluoride, in BF3, we have a pull from the boron to each of the fluoride molecules, or sorry, fluorine atoms. In carbon tetrafluoride, same thing. Carbon tetrafluoride would look kind of like methane, same basic tetrahedral shape. But where fluorine is so electronegative, the electrons in that bond are getting pulled towards the fluorine just a little bit. And so what we have to do is we have to try to determine if an entire molecule is polar or not. And so what we do there is we write out our Lewis structure, and then we start to consider the three-dimensional shape of the molecule. But then we often have to look for any polar bonds within the molecule. And so, for example, we would look at, so in our example maybe of, so here's our carbon tetrafluoride. Put in our lone pairs. Now we look at our electronegativity table, and you'll be able to use a table like this. You're not going to have to memorize electronegativity values. But we look for a difference that is 0.5 or more, or an electronegativity difference. So if we have an electronegativity difference of 0.5 or more between two atoms, we say that is a polar bond. And I forget what the values are for carbon and fluorine. I want to say I think carbon's 2.5 and fluorine is 4 maybe. So definitely a difference of 0.5 or more. And so each of these bonds is definitely a polar bond, with the electron spending more time near the fluorine atom. But now we have to think about the three-dimensionality to figure out if the whole compound is actually polar, because these polar bonds might cancel each other out. And in fact, they do in a case like this. And so we go through our sort of process here. So we first ask, does the molecule have any polar covalent bonds? Does it have any bonds at all where the atoms have an electronegativity difference of more than 0.5? If it doesn't, then the whole molecule is nonpolar, and that's easy enough to do. If the molecule does have some polar bonds in it, then we say, okay, does the molecule have more than two atoms? More than two different types? No, then it's definitely going to be polar. So something like HF or NO, only two atoms there, so the molecule will be polar. If it does have more than two atoms, then we ask, is the shape tetrahedral, trignoplanar, or linear? Are there no non-bonding groups on the central atom? If the answer is no, if it is something like trigonopyramidal or bent, then the molecule will be polar. If the answer is yes, sort of going through our flow chart here, then we ask, are they all identical? And so that would be a case like we have here. We have definitely more than three atoms. We have covalent bonds, but they're all identical and it's symmetrical. So they're going to cancel each other out. And so this is a non-polar molecule, as opposed to maybe CH3F. Now, our electronegativity difference between carbon and hydrogen is only 0.4. So that's not a polar bond. But we do have a polar bond right here. And so this is what we would call a polar molecule. Now, I know that that's not easy stuff, and that's not intuitive. Chances are, if you haven't read the textbook at all yet, you're sitting there going, huh? Go back and read the book. Think about the things that I've said here. Go back and read the book a couple times if you have to, and then try to piece this together. But ultimately, for what we talk about in the next video, we have to use our three-dimensional shape of a molecule. And so sort of a couple of different goals here. We need to use VSEPR to figure out ultimately, our molecular shape. There we go. And then use the polarity, possible polarity, to figure out, is the molecule, the entire molecule, polar or non-polar? And we're going to use that information in our next video. And so, like I said, I know this wasn't necessarily easy, and especially some of that discussion of polarity, it wouldn't surprise me if you had to go back and look at some things. But you can also, as always, check out the website. A couple different supplemental videos here. Here's one on just polarity that might help you out. And so that's it for this video. And in the meantime, stay classy, USM.